This is Anna Galactic bringing you another science presentation. We are currently in a sequence in which we're attempting to get a definition of the photon, which can also be stated another way, since the photon does have two different aspects which are baffling to science. We're attempting to get a definition of light, and by definition, what we are actually looking for is an expanded definition of light, such that the phenomenon can be understood to a sufficient degree to explain redshift. We must understand redshift. It turns out there are several ways of describing or explaining redshift, and the Wikipedia article on this topic brings out the depth and breadth of this topic, which is, to me, surprisingly broad. In other words, redshift is not merely a simple measurement. It's not merely that redshift establishes a linear relationship with distance in cosmic space. That is the celebrated feature of redshift, which makes the phenomenon of eternal importance in science, because it gives us the final rung on the cosmic distance ladder, whereby we can make determinations of distance from the redshift. This is tricky at close range. That is, in our galactic vicinity, the redshift relationship does not hold. Because of relative velocities in our vicinity, actually the Andromeda galaxy has a blue shift. And then I've noticed that according to my, I'll just say, theoretical approach to redshift, mostly to get at the cosmological question, the cosmological aspect of redshift, in order to understand that, to know what's being said by the modelers, I had to investigate much more deeply than I thought I would ever need to do the full breadth of the nature of redshift. And I have to say, I have to fully confess that even though I was fully prepared to take the deep dive, sometimes if you're homing in on something in science, you need to start doing some excavation. You need to understand this one thing much, much more deeply than you would need to understand anything else in your perhaps entire scientific career. And so I was prepared for that, or so I thought. But Wikipedia is a humbling experience. I've encountered this same phenomenon many times, but I'll be honest, again, I did not suspect that redshift was such a deep, 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 complex, complicated, convoluted, and cutting-edge phenomenon. Redshift, an entire Encyclopedia Britannica shelf could be filled with nothing but information about redshift, which I have got to say caused me to think, to kind of fall back. This has been a process for me because, of course, a scientist wants to get to the answer. You don't want to like shy back and go back to your tent and just meditate for a few days because you just can't handle it anymore. But actually, that is part of being a human. Sometimes you're all overwhelmed. Well, that's humbling. When you think, I remember a long time ago, I'll just say a quick story. I love to tell some stories, so let's get it out of the way. When I was younger, much younger than today, I never needed any science in any way. I was about, I believe, 11 or 12. I was in junior high, as we call it in the United States, at least on the West Coast. Junior high age bracket before puberty, 10 to 12. I was being taught science at a higher level than grade school, but not very high. I mean, we was learning about basically dirt in the sky and a few other things. A little bit of biology, a little bit of geology, but not much of anything. But by junior high, we were being, groomed to go on to high school, which is your grooming for going on to college, where you write thesis papers and you have to prove yourself by coming up with some kind of a proposition, scientific, and then show your research and experimentation if that's involved, and then reach your conclusions, and then you're evaluated on how completely, consistently, and coherently you did the job. Well, my first experiences in science were to have to write, it's either called homework or your project. Your project. It's kind of halfway between homework and an exam. It's like you work on it and you're expected to keep working on your project. And after a certain number of weeks, you submit, your work, and then you get graded. Brutal, brutal system. It was very, very unhappy, unfortunate, unfair, malignant system of torturing youths. But, that's the way the world works. The world is not fair or happy. It's just the way it is. And so we had to be graded. So, of course, you want to do well. Otherwise, you'll starve to death. You start to realize this is life and death. You need to start now, get going, do things the way you're expected to do them, which is, all right, so you got to choose a topic, right? Well, our topic today is time. And you would think, well, time, boy, that could either be philosophical or very precise, like, space-time. You're talking about a mathematical quantity, and whatever you say about time, it's in terms of space-time. Well, that's not philosophy. Oh, we'll get there. But my first topics I had to choose, well, the first one I chose was blood clotting, coagulation. Holy crud, I learned so much. But then there was another one, oil, petroleum. Vastly interested in the phenomenon of petroleum. Well, the long and short of it is I learned so much, but what I really learned, the real lesson that I took away all the way back in junior high school, is that when you scratch the surface of a subject, that you're going to find out it just goes on forever. It's part of the, you could call it beauty, I guess, but it's overpowering. That's the overall sensation. It's humbling. That when you go to study some subject, you think, well, I'll just write a couple of outlines and we'll expand the outline logically. Well, if your experience is anything like mine, and I know that I'm not alone in this, I think we all go through the same thing as scientists. You get to a point where you're expanding on one of your little topics, and holy schlemazel, it expands by itself. And then you go, and something fascinates you about, just like blood coagulation is actually a step-by-step process. That there are enzymes which catalyze the production of other enzymes, and it's as much as a 14-step process. It's been described as, although kind of there's different levels of this sequence. But you just thought, you scratch yourself and you get a clot. Well, it's magic. And of course, that's why I chose the subject. I wanted to know how blood clots. Because it has to be done just right or it'll kill you. And if it's done not quite right, you'll bleed to death. And if it's done a little too much, it'll go into your bloodstream and give you a bad deal. It's somewhere in the veins. So You can get an aneurysm or you can bleed to death, okay? So you don't want hemophilia and you don't want it to clot too much or just you have clots, you just turn into a clot and die. So, but it's, you think, well, that's the end of my paper, one paragraph. You don't want to bleed to death. You don't want to get an aneurysm. No, it just goes on for thousands and thousands of pages. And you just are writing this stuff down. My God, fibrin, fibrinogen, just K factors, just waterfall sequences of events that branch out into atomic molecular theory of how things work at any level. It just, and you end up studying time. That's really somewhat what is happening in science today. Is time is really, it's like a new circus event. It's like they built this whole new tent for people to come in and have a good time with science. It's like, well, where's the action in the science carnival today? Oh, you want to go to the time tent. The time tent. So rather than bore you with any documents on the screen or diagrams, which I am not too coordinated with, okay, I'm just going to read a little bit to you from a document. I'm not even going to show it to you. This is the article from Wikipedia called Chronoception. Here's where I got, just within the past few days in my studies in time, which I have seen time from many angles now, and I'm getting pretty adept at identifying bullshit arguments too, because you finally have to get tough. It's like, well, the eternal present is just the absolute negation of nothingness and implies the infinity that we all need to what? I believe that time is ultimately simple, but in space-time, it's not. It just isn't. It's tied in a knot with space. So, in trying to get a definition of time, you really do have to be specific about why do you want to have a definition of time. For the same reason that you have to justify anything in science, it's like, why do you worry about why the sun goes through the sky? It's like, really, it's kind of like, don't you have anything better to do? Which is soliciting value. It's like, why do you care that the sun, changes its angle throughout the year as it passes through the sky? Why are you out there with your telescope studying the stars? Why? It really comes down to the question of why do anything. I hope you and I are well past that. But when it comes to time, you just end up kind of returning to your sources. It's like, oh, it's happening again. That time is just a multi-level phenomenon, which is a strange thing to say. It's somewhat paradoxical, I think is the right word to use here, in the sense that a paradox is hard to put into words. Well, in science, the whole art is to do that. We'll put it into words to the best you can. And a good scientist is valuable for that reason. That's what I'm trying to be. At least to be valuable to myself. That is where it starts. You're trying to straighten out your own thoughts. How do I regard reality? It's meaningful. You have to assume it's meaningful. Well, for yourself, you don't have to assume anything. It is meaningful. But in science, it's consensual, collaborative, and communicative. We're not in this to be alone. We're in this to have a common understanding. For various reasons. There are various reasons why men want to put their minds all on the same page. Because if you're trying to build something, you certainly need to coordinate your efforts. Well, this isn't for building something. I don't believe that technology is the true aim of science. It's one of the aims of science. Obviously, it's one of the aims. I believe most people believe it's really the definitive aim of science is to build things. That is very difficult to argue with. So I don't. I just accept it because it is obvious. I mean, electricity, cars, jets, computers, cell phones, hello. Obviously, science is for technology. This is the result of rational logic. This is the result of consensual, communicative, collaborative logic. We're using logic. Well, if you get caught up in that, you can overlook your own life. You can dedicate yourself to the machine. I don't want to get into something Orwellian but really we are humans, and so you have to admit that you do have two sides. We do want to function together to be useful. Men, I'm just saying men, I always mean women. But traditionally we say men, and that includes women. I'm sorry, we're stuck with that convention. I've tried to find a way around that, but I'm not going to say men and women every single time. Because, my God, grow up. You know what I mean? But you also don't want to be misunderstood. But men pool their minds for any number of reasons. Well, it's ostensibly for good, but you also know that men can pool their minds for very localized good reasons. Like, I would have to say that the Ku Klux Klan, when they put their minds together to get something done, that's a very restricted idea of accomplishing something good, is to be in the Ku Klux Klan, or in a political party, or in a religion. It could be good, it could be bad. It's a totally human question, and it has to do with localization. Well, to get on to our topic, so does time. A consideration of time has to do with locality. This matter of locality just keeps coming up. It is one of the fundamental terms in quantum mechanics. So as we turn our attention again to time, what I am attempting to expose now about any conception of time is that it is now a mathematical quantity. Albert Einstein did that. It used to be, before Einstein, I think this is a fair way to put it, that time was a virtual quantity. It's simply a progression of events that's continuous. I think we all know that. In fact, in my lucubrations, in my meditations, as I've kind of fallen back, just to regroup a little bit, because some of the things that are being said now in physical science, which is ordinarily ultra-rational, are just off-the-wall philosophizing, and some of it is quite misleading. There's misleading conceptions of time. There are even broadcasts out on YouTube right now, and whole books written, which have at least as a partial premise that time is unreal. Time is unreal. How in the world? Well, this is exactly the reason for this particular presentation, is to give you, as well as myself, I'm sharing my consolidated view of what's going on in science that really is borderline psychotic. I mean, some of the things that are being said, I'll just sum it up in one phrase: is time real? That is the title of the PBS production. It's called PBS Spacetime. The presenter is very good, and I have never identified his origin, his accent. I don't even know his name, but he's a very good presenter. But like most presenters on YouTube, he's looking for viewership. That's normal in entertainment. This is entertainment. But it's entertainment in the name of science when it's not. I don't want to feel jealous because I don't have any jurisdiction over science. I'm not trying to protect science. What I am trying to protect is a rational inquiry, I guess you'd say status or mode or level, a level of accountability in what are we doing when we start talking about time as being unreal? Well, I'd like to start at the other end of the spectrum now that I've thought about it deeply and slept on it. That you could start out in defining time as stating that it is one of a very select few phenomena, or just sometimes we just say things. The world is so full of a number of things. Well, it is full of time, that's for sure. And what is it? How can you define time scientifically? Well, one way to begin would be to say it's axiomatic that we all know what time is, and it only has one definition, and it never changes. And it's the most stable concept of all, that time does not bend, that time does not change. There's nothing mysterious about time. There's nothing you can even say about time. I think you see the hole in that argument. There is definitely something you can say rationally, logically, and scientifically about time. Albert Einstein certainly did. But it's important to see where that hole exists. There is a hole in what we think of as ordinary common sense. Commonsensical time is a valid way to define time. It's not the only way to define time, and it may not be the most useful way to define time. In other words, we do want to understand time for a very good reason. Well, what is that reason? For me, it has to do with the cosmological interpretation of the universe. That is, how do we understand the universe? Well, if you're trying to understand the whole universe, which already you need to be cautious in even approaching that topic, because it's very difficult to define what is the universe. Well, is it? It's about as difficult as defining time. It's about as difficult as defining space. Because from one aspect, which I think must be borne in mind, time is obvious. We all know what time is, and we never disagree about it. In fact, well, I could go on, but that really is a philosophical point of view. Okay, well, that is part of life. In our ordinary, just day-to-day existence, we take time for granted. We all understand time. If you are pressed to give a definition, you could. It's a sequence of events. And then if you want to play angels on a pinhead, it certainly has been done throughout the centuries. But I don't think you're going to get anywhere. And the eternal now and the kairos and the chronos, what's the difference between this kind of time and that kind of time? It's been proposed that there are two orders of time. There are definitely differences in local time, separated by space, which actually is also separated by time, so it can get complex pretty quickly. But you do have to have a goal in science if you're going to, otherwise it's philosophy. Philosophy is interesting to me because it has no goal. Well, science does have a goal, and even that's arguable in both ways. So we're kind of on a floating island that just, this is a malleable, ductile, fluid state that we find ourselves in trying to reconcile science with regular life. Where that becomes clarified is when we have, for instance, the harnessing of electricity. That shows a practical value of logic, as you never would have guessed at how to harness electricity from philosophy. Eventually you have to get down to hard brass tacks, which is measurements, which means numbers, geometry, angles, precise calculations, and manufacture, the molding of materials such as metals into certain shapes that have certain characteristics, to make a boiler to make a locomotive, to then generate power for electricity to light people's homes, to create heat in their homes. This is of enormous value to humans. What about a consideration of time? Well, I can point to something right up in the sky right now over our heads, which you're aware of, which would not be where it is. This is the James Webb Telescope. Yeah, all astronomers are aware of that thing out there, and most of the rest of us are too. That thing would not be there unless there had been a scientific understanding of the relationship between time and space. That's a fact. Only with Albert Einstein's relativity, in both of its forms, special and general relativity, which has to do with frame of reference, for time. It's a reconceptualization of gravity with time woven into the fabric of space. That is necessary due to the time lag over volume space. That James Webb Telescope, no matter how you slice and dice time and space, the local time on that telescope is not the same as local time on Earth. And if you think that it is, such that when you broadcast a command to that craft to make a minor adjustment in its Lissajous orbit so it remains where it is, parked in space, that's a Lissajous orbit around an Euler point, commonly called a Lagrangian point today. And that's a parking slot on the other side of the moon, but every now and then you have to fire a thruster to maintain that very delicate orbit. It's not much, but you still have to maintain the orbit. And so you have to issue a command, presumably or mythically from Houston. We'll just say it's from Houston. I don't know, it probably is from Houston. I actually don't know, but I would say it's at least as likely that it's Houston as anywhere else. So Houston sends this command. Well, it takes a few seconds because it takes time. Yeah, time. It takes time for the light. It's a form of light. It's radio, but that's part of the light spectrum. I think it's radio. Or whatever it is, it's in the light band, and so it travels at the speed of light. But it doesn't get there instantaneously, and so you have to compensate. And this becomes much more important, for instance, for the various craft which were sent to the far planets. For instance, I always want to say the Huygens craft, but I don't think it was called the Huygens craft. The deep space probe that we sent to Saturn. My goodness. Well, I am getting old, so I don't often remember a proper name correctly. What was the name of that thing? Well, I'm sure you know what it is. But it's one, well, there's many of them actually, but there's one famous one. Not the Huygens craft. Cassini. There we go. I can edit this too, so I won't. No, you have to be able to admit errors to be a scientist. They're going to continue. You just hope that they're less and less severe than the errors that you made before. So time has this characteristic that it's of great importance in science in a practical way, that there's such a thing as time lag over volume space. It's hours for a command to reach the Cassini craft around Saturn. So you have to make sure that your boys who are doing the calculations to tell this thing it does have to use thrusters to change its course from time to time. And so you can't just say, well, tell it to turn left, 20 degrees. Because you've plotted it on Earth. No, and in fact, you're not sure where it is, because when it sends its position measurement back to you, it tells you where it is, or you're getting a fix on it, you're getting a fix on where it was a couple of hours ago. So you have to know that to begin with, and then when you tell it to change course, you have to make sure You're plotting it to be 2 hours in the future. Well, 2 hours in the future? And you're talking about a position? That's space-time. You have to have both. And if you can combine them both into space-time, that is space and time, oh, you got a powerful tool. Well, that's the only reason that the James Webb Telescope is parked where it is. You can't do it without relativity because of time. So time is not just a philosophical parlor game, but unfortunately or happily, depending on the situation, it's also a marvelous parlor game. It's almost irresistible that as you probe time, you start to think about all the things that the ancient philosophers thought about. Is it continuous? That's what we'd like to talk about today. And that's a half an hour, so that's our introduction to time for today. I have been broadcasting over these past 2 years that I have the best definition of time. But I'll tell you what, it has changed. So, somewhere in that process, I have had to absorb more knowledge and somehow synthesize more understanding about time, which has been progressive and is not over yet. But my goodness, to have a proper interpretation of time is critical now. It goes way beyond space-time. We're talking about the quantum mechanical paradox. It turns out, according to my research, which, again, just when you think you have it, there's more. It keeps telescoping. Well, in this telescoping process, we're in good shape because we're going in. That is, I am. But it really is a collaborative effort. It's not just what I'm doing. This is going on all over the world. Everyone's trying their hand at this who feels drawn to it or compelled to it for whatever reason to understand time. Well, you need to be careful of your framework. And you also need to be careful of a lot of details. Because in the quantum paradox, how does time figure into the quantum paradox? Would you be able to write a brief essay on that right now to submit it to some professor? Not me. I don't test anybody. But would you be able to? You ask yourself, would you be able to give a short or even a long dissertation on the role of time in the quantum paradox? You've heard of entanglement. It's a spatial separation of two particles in an entangled state, which simply means that they're coordinated. Entanglement is a stupid name. I'm sorry to have to use the word stupid. But it shouldn't be called entanglement because that sounds complicated. All it means is that you have two particles that have a possible state, or different states, but you choose one state and you synchronize them so they're both in the same state. Well, they're both pointing in the same direction in their electromagnetic orientation. Some state that you combine them. It's not really entangled. There is actually a reason for that word, though. Because of the logic system involved goes beyond our linear and binary logic system, it's called superposition. But if you have, normally the two particles are unrelated. They don't know each other. But if they're both put into the same kind of state, this is specific to certain states. And it really has to be an electron or a photon, which can be polarized or, I'll just say magnetized, a general word, where their state has been coordinated. But here's the thing. When you take these two particles that now have a definite relationship with each other and you separate them spatially so that there is a time lag, Because there is always a time lag, but now you just make it more because time goes pretty fast when you're talking about light. You're talking about the speed of light that's very hard, it's really fast. So if you separate what you're trying to measure, the change of state over distance, which is a time lag, it can be shown, although this is still, well, it's spooky, but the nature of entanglement is these two particles, which are in a coordinated state, which we call entangled for various reasons, but I'll just say coordinated state. When you change this state, essentially by measuring it, you take a measurement on this particle, it fixes the characteristic of this one. That even though the two are in a coordinated state, you're not sure of the exact description of the coordination, but they are coordinated. And the way you know that is when you take a measurement on this one changes. And that's transluminal. That's superluminal transmission of information, it was thought. It turns out it's not exactly true. It stays spooky because there is some, I'll just tell you out of the box, I'll tell you the right way to look at, there's a geometric connection between them, which is not spatial. And so, according to the way we look at space and time and space-time, according to Albert's speed limit of the universe, there can be nothing that travels faster than the speed of light. And so the entangled state shows a violation of special relativity for that reason. Well, it actually doesn't. But in order to prove that it doesn't, you have to see the situation geometrically. And that's what's really, really missing. This has been pointed out explicitly using the word geometry. It was Tim Palmer. I haven't seen this said more than 2 or 3 times in all my research of quantum mechanics. That part of the paradox has to do with a notion of time. It's a notion of time, but what I've discovered is you can think of that in order to get a visual understanding of entanglement, is that they're related geometrically, but not in space. That would be new in physics. If what I'm saying is true, that's new to physics. Well, that's one possibility that is not brought up too often. And to complete my former sentence, I do not see geometry mentioned ever. It's like it's gone in cosmology. They never talk about geometry. And in quantum mechanics, just never. The subject does not come up. It's all mathematical. It's all numeric. Well, there's where the paradox could be located. I have located the paradox, the source of the paradox. But this paradoxical system is actually a system, and there are different ways of pinpointing what is causing the paradox. It shows up in different forms. The paradox. What is a paradox? It's an inconsistency in logic that seems inescapable. Usually it's a contradiction, but it's peculiar. And this is worthy of some discussion. I'll just give this to you to think about for now. Is that there are 2 forms of paradox. One is a simpler form where there's a direct contradiction between the 2 things that can be proved. You can prove one thing, but you can also prove something else, but they're contradictory. That produces a paradox called a logical contradiction. If it's physical, as it would be in the case of quantum mechanics, then it's paradoxical, because logically you can't justify the existence of both conditions. This is the wave-particle duality, but not quite, because it's not an exact contradiction. Instead, in the standard or simple form of a paradox, they're contradictory. So it's really the binary relationship between true and false is violated. There's another way to violate that without a direct contradiction. You you have two things that are true, but they can't be true at the same time. And there's the word time again. When we make a quantum experiment, you're looking at two successive states of the same particle. Usually it's a particle. Not always, but, well, yes, actually a particle is at least implicitly involved at all times. But you're really talking about state. And it's just, this is why it's useful for me to talk about this with you, or to you, because I hear myself struggle with this. And you'll see this a lot with top-notch presenters who are worried about their reputation, so that's one reason they hem and haw a lot. But they're actually wrestling in their own minds, so they stutter and spit, and they're not very good speakers. Well, neither am I at this moment. Let me go on. You're measuring one state, and then that's a measurement. And then you measure it again. Or you measure two states, but there's always an interval. And in the case of entanglement, what you're trying to do is prove the interval to not exist. Because, and this can be proved, that there is no interval. In other words, something is happening that defies the speed of light, because there's always an interval in space-time. You can't have absolute simultaneity at any distance, except by coincidence, you could say. But if there's a coordinated change, so that one state changes and the other one changes without any time lag, that's considered to be a violation of special relativity. Well, that's hard to deny, but we may be framing the question incorrectly. Because why does there have to be a time interval? This is called, or this is part of the hidden variable problem, or aspect to the problem, which Einstein brought up. This is generally attributed to Einstein because he's the one who made the biggest deal out of this, that in a time interval has to exist if there's a spatial interval, that you can't have coordination between two events without a time differential. That seems obvious. I would have to say that's fairly reasonable. Otherwise, something that happens on Mars and something that happens on Earth could be connected in a non-causal way. Well, that's called synchronicity, but that's a philosophical concept. It doesn't really belong in science. Well, we discovered something like it in science. But if you look at it, just step back and just think about it. Here's the Bob particle and here's the Alice particle, okay? Named after those who are going to measure it, yes. And this state is measured, and then by using a complex apparatus, which is very difficult to set up and coordinate, you make sure that you check the state of the other particle before any time has elapsed. So you got to be quick. But what can be shown, and has been shown by very difficult to execute experiments, is that the states do change simultaneously without any conception of spatial separation. In effect, there's no spatial separation. It's as if they were the same particle in that sense. That in the state that they have originated when they were bound together in that state, usually with some, it can be done, there's different ways of binding the two, synchronizing them. And then you separate the two particles, but they are still synchronized. But now that they're far away from each other, yeah, maybe they're still synchronized, but changing one won't change the other except if there's a communication across the distance. Well, that does not occur. So that is spooky, very spooky. And I am certain that I have the right aspect on it, but what makes this permanently spooky, and no one will ever, or nobody so far has been able to nail down what this relationship actually is, it's because of a limitation in us. We literally cannot see certain things. And you're aware of this. We only see a certain small part of the waveband. We can't see infrared or anything lower, radio or anything like that. And we can't see ultraviolet or anything above it. But we can detect them with instrumentation. Now, one thing that we cannot see ever is infinity. And that is a paradoxical thing to say because we have been progressively seeing a lot of infinity. But that's not the definition of infinity. We're seeing progressively more of the visible universe, but there's always more. So that's something we simply cannot see. It's hard to even imagine what you'd have to be to see the all of the universe. You'd have to be some kind of being that we can't even really imagine. So that's something we can't see. We're physically limited from seeing infinity. We just can't even define it, really, although I have. So science is the art of progressively getting better understanding for a purpose, for usefulness to us, in this case, simply to get the answers. Now, that's not enough to say, and I've spent several lectures over the past 2 years talking about why we do this. It is ultimately religious. Let's let the cat out of the bag, okay? You may not be religious. That's entirely your business. This isn't the Vatican talking to you and telling you what to do and how things are. But you do have to develop your own religion, or you will simply never be a complete human. You must have your own religion. And what would that be defined as? Dealing with that which you may want to deal with but can't. And so you have to somehow explain it to yourself. What is life after death? Well, you could say, well, it's absurd. Well, that's your religion. What about a great designer that just designed all this stuff? Well, I just don't think that's... You're an idiot to think that. Okay, that's your religion. Larry Krauss has no problem saying that. I mean, it's not just Larry. There are professional religionists whose real goal, such as Dawkins. Dawkins is a very good example. He's very typical. He's simply a very eloquent, religious person. He's extremely religious. He's one of the most religious people I've ever heard dare to open his mouth and attempt to be taken seriously. Because he starts out by declaring that he just is absolutely without a clue. He just doesn't know anything. And he's proud of it. And the way he says, he announces his religion and he wants people to read his books because he has a very powerful aspect on reality. There is no God. My father actually subscribed to this to a certain degree when he said to me, one of the only religious things he ever said to me, because he knew I was reading the Bible, and he never objected, but he never asked about it. But one day he just said, it was just off the wall, it wasn't anything adversarial. He just announced himself to me, and it made sense at the time, but I've been unable to reconstruct the context. Because I think I was traumatized even to hear my father say the name of God, because I knew he was an atheist. He didn't have to tell me. He never talked about God. Well, it didn't mean he was an atheist. A very good man, very moral man, nothing wrong with him. But one day he said to me, "There's no old man in the sky." And I don't talk back to Dad. That made perfect sense to me. I nodded. No, there's not. There certainly isn't. Well, there might be, though. Depends on what you mean by old man in the sky. He has been called the Ancient of Days. He has white hair. I'm pretty sure that that's not literal, but who knows? I mean, I don't claim to know that. What I do know, and I've always known, both from religion and from science, that is a religious point of view. All religion is a framework where you fill in certain things that people find difficult to fill in, like the reason why, your sister got a rash on her arm. It was a demon. I mean, I'm not sure that's very scientific, and I never thought that. But I knew that some people were of that opinion. Oh, that's a demonic infestation. You're going to need an exorcist. I'm not sure we live in that day and age, but I can assure you from what I've seen, oh yes we do. Time is unreal. Who in their right mind would say that time is unreal? People very serious about getting scientific answers about reality. That's what we'll be talking about, is the nature of time, a better definition of time that has to do with the electron and the photon, and ultimately reality. That time definitely is part of reality. It's definitely a geometric sizable concept. Einstein proved that. He did it inaccurately because he was stuck with lines. And time, just to give you something to think about, time, although it's it's linear, right? Yes, it's linear for local time, which is what all time ever is. It's local time. Unless you're trying to talk with something near Saturn, in which case you're going to need the conversion between two local times, both of which are moving. That's very difficult to do. That's why the Einstein field equation is very complex, but it's very helpful. It helps bridge that gap of the time lag over volume space. Well, what does that mean in terms of reality? That's where it gets harebrained. But time is considered to be linear, but I'll tell you the secret of time, not the secret, but for now, one secret, is that time is a derivative concept. Space is not. Space is absolute, and we know that from the proton. That's a space particle, and in that sense the only particle. But then we have the electron, which is not at all like the proton, but they are related, and they do have a relationship. What does it have to do with time? Time is manifested by the electron, but not directly, because everything about the electron is spherical, and it's motion, so it's angular momentum. It's that angular momentum that generates the perception of time in real space. So that would be real time, is based on this cyclic motion of the electron. That's transferred to the photon, which then has the absolute characteristics of space and time involved in its very nature. Because now it's absolute. It's no longer locked into a particle, which is really an antiparticle. The electron is an antiparticle, because it's not spatial. unless you think of the sphere, the bound sphere, which is pure motion, pure angular momentum, that's actually a different dimension of space. And it's the only other dimension. But it's not of space. It's the dimension of energy. And energy is pure angular momentum which exudes a force. Energy exudes a force. It's called centrifugal force. That goes out. And as it goes out, it's linearizable in one of its aspects. And that linearization of angular momentum to get the aspect of centrifugal force that can be felt, that's time. It's the linear derivative of a spherical function in another domain. And that's 55 minutes. We'll be back with more today. This is Thursday, February 22nd from Chico, California. This is Anagalactic, bringing you the secrets of the universe as I have been doing for 2 years. Close to 450 videos now. More than half of which I've made private. Those are outdated. They only got like 3 views. But lately I've been getting, I have as many as 300 views in a couple of my presentations. So I'm gratified that after 2 years of work I'm getting noticed. I have an increasing number of followers. But really, this is good timing for all, because it took 2 years for me to get this far, and I thought that I had something to offer 2 years ago. Well, I did. It was a new geometry with a new number system, which is necessary if you're going to have a usable new geometry. And I considered it to be extraordinarily valuable, but what I found out, it's been extraordinarily valuable to me. So I'm sharing that with you with all the discoveries that have come since, which have just rocked my boat. I'm the happiest man in the world in one sense, but I'm also quite busy with this. I wrote something recently just to straighten out a lot of the aspects of what's being discussed today about time. A lot of it is, you can feel how close these men feel that they're getting to the answer. But the range of guesses is absolutely fantastic. Worth a study in itself, and there are books on this, on just which ones of these theories are totally harebrained. What is leading men to have all of these opinions about time? It's because we're homing in on the quantum paradox. I have been claiming for 2 years, well, about 1 year, I've been claiming that I've got the full insight into the quantum paradox. I would like to just humbly reframe that. I'm getting better and better at describing what is the quantum paradox, such that it can be absolutely proved what is happening. That is what everybody wants. And I keep saying that I've got it. But each time I say that, of course I'm curious to know more. I keep getting it to a better and better threshold. So that's an hour. We'll be back. Today I need to tend to my life. But this is what I do now. I've been doing this for 2 years, and thank you for tuning in. I hope you're having a good time. I certainly am. But don't forget, this wouldn't be interesting if there weren't any bumps in the ride. So we'll be right back. Keep looking up when the sky clears. And this is Anagalactic.